Today we're going to talk a little bit about radioactive decay. So far we've learned that radioactive reactions occur in the nucleus, not the electrons. We talked about the band of stability and which atoms or isotopes are more likely to have a nuclear reaction and which ones are not. And today what we're going to do is we're going to talk about how the nucleus spontaneously reacts to form a more stable nucleus and actually forms a different atom. For example, uranium-238 actually becomes thorium-234, a completely different atom. Uranium has an atomic number of 92, and thorium has an atomic mass number of 90. So how can that happen? So let's talk about it. There's three kinds of radioactivity. There's either an alpha particle, a beta particle, or a gamma ray that is given off. We've kind of talked about alpha particles already. We talked about those with Rutherford, and it's a helium 4-2 atom. So let's talk about that. I know that the pictures on here are not quite as clear and easy to see as they are on the PowerPoint that I printed out for you, but hopefully you can just follow along with me. Okay. So, an energetic helium nucleus, which has 2 protons and 2 neutrons. It is charged and relatively heavy. It is a +2 charge because it's lost both of its electrons. It's easy to stop. A thin sheet of paper, your skin basically stops it without a problem. The reason is because it's a large particle, so it cannot fit into small places very easily. And it has a positive charge. So as soon as it hits a cell that is not charged, it actually absorbs and the cell will give it its electron so that that alpha particle is no longer charged. It reacts really quickly, turns right back into helium. So as far as a skin injury, it will cause a burn. But other than that, it doesn't cause a lot of damage internally unless you inhale the particle. Because now, instead of it being a burn on the outside of your skin, it's actually a burn on the inside in your lungs or your esophagus or your mouth or wherever it is. So that's what an alpha particle is. A beta particle, it's a high energy electron that's given off from the nucleus and is formed by the breaking up of a neutron, which is normally neutrally charged. So think about it. If a neutron does no charge, it has to have a positive part and a negative part. So what happens is that proton is split from the electron. Okay, so what that means, it's a negative charge. It's a much smaller particles because it doesn't have all of those protons and neutrons that we have in the alpha particle. We don't have those. So it's a lot smaller. As far as danger, it's lighter. It's less charged. It's only a -1, not a +2. It's harder to stop. It's smaller. It can get through little spaces a lot easier. So it can get through your skin and do damage. It's a little bit harder to stop as far as it's not stopped by paper, but it's actually stopped by wood. So if you're inside your house and it's wood on the outside, you would not be exposed to beta particles. Okay, we'll talk about the symbols a little bit later. The last one is a gamma ray, and it's an energy burst from the nucleus. No matter, no charge. It's not a particle. It's a wave. So because it's a particle, not a particle in a wave, think about radio waves. They go in your house, right? That's how you can tune your radio in from the old days. So it's much harder to stop. You need feet of concrete to stop it. And if you're outside or exposed to it, it can actually cause much damage to your whole entire body because it can penetrate through that. So here's a picture that kind of shows whether it's alpha, beta, or gamma. So let me put these in here. Let me try and put them in red, see if that will show up. This is stopped by paper. Then that's going to be an alpha particle. If this is stopped by glass, it's going to be beta particle, and then this is kind of your weird gamma particle. I'm not too good at making a gamma particle thing, but that's basically what it is. Okay, so it's either stopped by paper, glass, or lead. I don't know, maybe it would be easier to see it down here. This is the Greek symbol for alpha. A beta particle is just kind of a weird B, and then a gamma particle is kind of more like a cursive Y. Okay? Alrighty. Question. A beta particle is just a blank that leaves the nucleus. The answer there is 3, electron. A beta particle is just an electron that's leaving the nucleus, which is totally foreign to anything we've talked about this year. We only talked about the electrons being circling outside. So remember that proton or the neutron is actually changed into a proton and an electron. Okay. The atomic mass of an alpha particle is, remember, it's helium-4, So atomic mass is the larger number. It's the number of protons and neutrons. So it is helium-4, if you remember this. So it is 2 protons and 2 neutrons, but 0 electrons. Alrighty, what about the atomic mass of a gamma ray? Atomic mass of a gamma ray is actually 0. Why? Because it's a wave. It's not a particle. So those are the 3 types of radiation that is given out. You're going to need to know for the test as far as which one is positively charged and how much, which one's negatively charged, which one's not charged, which one is the largest, which one is smaller, which one is not even a particle. All of these kind of questions that we just went over, and also, of course, which one is the most damaging and that type of thing. So now we're going to skip through a little bit. We're going to skip through measuring radiation. We'll talk about that when we talk about power plants and fission and fusion a little bit later. But I want to get into basically just the actual equation itself. Okay, we'll come back to this a little bit later. So if you can flip, we are now down to page 6 in your notes. Nuclear equations describe splitting, fusing, or particle emission. Include a nuclide, a specific and a specific isotope of the element. So let's take a look at it. Okay, so this is a particle emission over here. Here's your helium-4, so we know this is an alpha particle. So this is alpha decay. So the atomic number is going to drop by 2, and the atomic mass is going to drop by 4, correct? Because this is what's given off here. We're giving off a 4, and also we're giving off a 2. So that means uranium-238, 238 minus 4 is 234, 92 minus 2 is 90. All right, let's take a look at fluorine in a little bit closer detail here. We're on the top of page 7. So if you remember fluorine has an atomic mass of 9 and a mass of 19. You're going to need your periodic charts for these exercises because you're going to have to figure out when it changes into a new element, what is it changing into, okay? So this is the nucleus before. We have 9 protons and 10 neutrons. So remember, fluorine kind of looked like this. The larger number was on the top. That's the number of protons plus neutrons, and the number of just protons is on the bottom, and that was the identity of the element. So in the slide, it's drawn out for you here. You can see the yellow positive are your protons, and the neutrons are 10, and they're the blue, and there's not charged. So the atomic mass is 19. So hopefully remember when we talked about that band of stability, and we said when the atomic number is less than 20, there should be an equal number of protons and neutrons, but there's not. There's 1 extra neutron. So that's what makes fluorine a little bit unstable. So after alpha decay, you have to know either I will tell you alpha decay and you write the formula, or I'll write the formula and you have to tell me what's actually going on. So if I'm telling you it's alpha decay, here's my alpha particle. 2 protons and 2 neutrons. That's what's given off. If you take 2 protons out of there, we didn't take any electrons out. Correct? Okay, so let's take a look at what happens. So in this case, let me come back to that. If it is 7 protons, now we have nitrogen. Okay? Alrighty. This slide is just showing lots of question marks. It's saying, hey, you got to think like problem solving. This is what the equation is going to look like. You're going to have something here, and something here. Okay, and that's what those question marks are trying to show. Alpha decay, if I tell you alpha decay, then you know that this has to be one of the products. Alrighty, so if you're given that uranium-234 is the reactant and that it is alpha decay because of this, okay, this is alpha decay because I started the equation for you. This is what you're given, you know you give off. So it's kind of like a math problem. You're going to subtract 2 neutrons and 2 protons. Okay. So here they've written it out as A and Z. They're just trying to they take this a little bit slowly on this PowerPoint to try and say, okay, what are we trying to do? We're trying to find a missing element. What would the atomic number be? And what would the mass number be? Remember that there's a difference and that the larger number is always on the top. Okay, so the mass number will be on the top. Okay, let's go down. The sum of the mass numbers and the atomic numbers must equal the mass number, right? And you have to add them all together. So it's not that difficult. They go through a lot of steps to do something that I think is quite easy. But something plus 234, right? Some number plus 4 has to equal 234. Basically what you're doing is you're doing 234 minus 4 and getting 230. Over here you're doing 92 minus 2 and you're getting 90. This is kind of hard to see, but it's supposed to be thorium, 230, and 90 on the bottom. So you're like, well, how did you know it was thorium? Because if you look at 90, once you subtract 92 minus 2 and you get 90, then you look on your periodic chart and you say, if it has an atomic number of 90, what atom is it? Okay, and you look on your chart and it says thorium. So that is alpha decay. Now let's do beta decay. The atomic number is going to increase by 1. Remember, a beta particle, the neutron is changing into a proton. So the neutron is negative, or a neutral charge, no charge, but you're making a proton. So now you got an extra positive charge. But a proton and a neutron are both counted the same weight in your atomic mass, so the atomic mass isn't going to change. The identity of the element is going to change because we're changing that atomic number, but we're not changing the mass, okay? So in this case, here's my beta particle, and you're going to have to get used to, like, that's how you show a beta particle. The reason why it's a 0 is because it has no mass. It only has a charge. So this is a really, really tiny particle, okay, with basically hardly any mass. Remember, it is more dangerous. It can slip into places and hurt things much easier than an alpha particle. So if we start with 14 and one of those neutrons changes into proton, I still have atomic mass of 14. This is going to stay the same. But because that the neutron changed into a proton, now this increases by 1. So we have a new element. 6 plus 1 is 7. You look on your periodic chart, say, what is 7? Oh, that's nitrogen. Okay, so let's do, this shows you fluorine again. So if fluorine goes through beta decay, this is what it looks like before, just like our alpha particle before alpha decay. You have 9 protons and you have 10 neutrons, and the atomic mass is 19. In this case, you end up with 10 protons and 9 neutrons, because one of these neutrons up here becomes what? A proton and an electron, because a proton and an electron gives you a neutral charge. The electron's given off. You see this beta particle down here? It's basically an electron with no mass, but it's not coming from the outside, from the electrons that are circling. It's coming from the inside of the nucleus. Okay. So we're going to, let's see, let's flip down to aluminum 28. So if aluminum 28 is the reactant, and I tell you that it's going to go through beta decay, well, what happens? What happens to that? Remember, in beta decay, the number on the top does not change, but the number of protons does change, so the identity of the element is changing. So let's show that they're working it out here. Okay, all right. Aluminum 2813, you end up getting 28. Remember the mass number is staying the same? Maybe it's easier to, no, it's not. This should be a 28 on the top. And then on the bottom, we get 13 plus 1 equals 14. So we have the number 14 on the bottom. So then you look at the periodic chart and you say, what is that? And that's silicon. This is your notation for your beta particle. It is a small b in this case, 0 mass and -1 charge. So that is beta decay. All right. We are skipping positron and electron capture, positron emission and electron capture this year. So we just have one more to do, and that is the gamma equation. So this one, the part of the notation for gamma is this. There's no charge and there's no mass. Why? Because it's not a particle. It's a wave. Okay? So that's what happens. Only energy is leaving the nucleus, but a lot of energy. A lot of energy. Okay? We're going to kind of stop there. So in this case, notice nothing left but energy. If there's no mass, then 99 doesn't change and 43 doesn't change. So it is the same element, but gamma energy is actually leaving the nucleus. We'll talk about that a little bit more later, but basically I wanted you to just be able to understand the equations. We will go over the equation worksheet in class tomorrow that I had handed out and do those six nuclear reactions together. But hopefully this will help you, and if you get confused, that you can go back to it at some time. All right, thank you and have a good day.